Just like economic models are simplified versions of reality, a graph is a simplified visualization of reality. An example of a graph is a street map. In economics, we are often interested in knowing how different variables are related to each other. A variable is just any value that can vary. Price, quantity demanded, income, age, and time are all examples of variables. And such relationships between variables can be expressed in a multitude of ways. They can be expressed verbally, via a table, mathematically, and graphically. The focus of this section, of course, is on how we can express the relationships between variables graphically. Most two-variable graphs are built on the Cartesian system, which is shown to the right. And this is simply just a grid built around two perpendicular lines that intersect each other. When graphing two variables, one is called the x variable and the other is called the y variable. The y variable lies along the vertical axis, and it's also known as the y-axis. The x variable lies along the horizontal axis, known as the x-axis. And the point where the y and x-axis cross is called the origin. At this point, both x and y are equal to 0. So starting at the origin and moving right brings us along the x-axis, where the values of x are positive and getting larger. So you see here 0 to 1 to 2 to 3 and so on. Starting at the origin and moving left brings us along the x-axis, where the values of x are negative and getting more negative. So from -1 to -2 to -3 and so on. Starting at the origin and moving up brings us along the y-axis, where the values of y are positive and getting larger. And finally, starting at the origin and moving down brings us along the y-axis, where the values of y are negative and getting more negative. You'll notice that in economics, we like to focus on quadrant 1 because most economic variables are positive. For example, income, age, time, price, and quantity are all positive variables. Any point on the graph or the quadrant is a coordinate, and it shows us an x and y pair, which is generally written as x comma y in parentheses. So let's go ahead and graph our data from the hot chocolate survey. To the left is the data that we collected from before, and to the right is the positive quadrant. Let's define the temperature as the x variable and plot it along the x-axis. And let's define the number of hot chocolates as the y variable and plot it along the y-axis. Let's start with point A. So when the temperature is 0 degrees, the number of hot chocolates is 75. So to graph that, I don't have to move anywhere. I'm already at the origin on x equals 0, and I have to move up along the y-axis by 75. When the temperature is 10 degrees, the number of hot chocolates sold is 65. So to graph this, I'm going to move along the x-axis by 10 units, and then I'm going to move up along the y variable by 65 units, and this gives me point B. Now when the temperature is 20 degrees, the number of hot chocolates sold is 55. So to plot point C, or coordinate C, I'm going to move along the x-axis by 20 units and move up along the y-axis by 55 units. And this gives me point C. And you can go ahead and plot the rest of the points, D, E, and F. And we can connect these points to make a line. Most graphs that depict relationships between two economic variables represent a causal relationship. A causal relationship between x and y exists when the value taken on by x directly influences or determines the value taken on by y. So in this case, the y variable is called the dependent variable. It depends on x. X variable is called the independent variable. In our example, the number of hot chocolates sold is the dependent variable, while the outside temperature is the independent variable. Quiz yourself. Determine what the dependent variable is and what the independent variable is in the following scenarios. We'll do the first one together. The higher is a degree earned, the higher is a person's salary. In this case, the dependent variable would be the salary because it depends on the level of degree. So the independent variable would be the level of degree. Pause the video and try to answer 2, 3, and 4 on your own. For the second one, when the price of a movie increases, less people go to the movies. Here, the dependent variable would be the number of movies attended, while the independent variable would be the price of the movie. As the average income in a country increases, the level of pollution rises. Here, the dependent variable would be the level of pollution, and the independent variable would be average income. And finally, when the availability of health insurance increases, the probability of being obese rises. In this case, the dependent variable would be obesity rates, and that depends on the independent variable, which would be the availability of health insurance. By convention, we put the dependent variable on the y-axis and the independent variable on the x-axis. So in our example, we've put the number of hot chocolates, that dependent variable, on the y-axis, and we've put that temperature, the independent variable, on the x-axis. This is normally what we do. However, you'll notice that there is a very important exception to this rule. When we show the relationship between the price of a good and the quantity demanded of the product, we usually put the independent variable, the price, on the y-axis and the dependent variable, the quantity demanded, on the x-axis. And the same is true when we show the relationships between the price of a good and the quantity supplied. So here's an example of figure 1a.3, plotting price and quantity points in a graph. So here we see that the independent variable, that price, is actually on the y-axis, and that the dependent variable, quantity, in this case pizzas per week, is on the x-axis. Interpreting a graph. Often, we want to know if the relationship between two variables, x and y, is positive or negative, and if it's linear or nonlinear. Two variables have a positive relationship when an increase in the value of one variable is associated with an increase in the value of another. For example, when the temperature increases, the quantity of ice-cold lemonade sold increases. So we see this positive relationship between y and x. Two variables have a negative relationship when an increase in the value of one variable is associated with a decrease in the value of another. So for example, when the temperature increases, the quantity of hot chocolate sold decreases. So here we have a negative relationship between x and y. It's also known as an inverse relationship. This is figure 1a.6 from the text, and it's giving an example of a positive relationship between income and consumption. This figure shows the positive relationship between disposable personal income and consumption spending. What this means is that as disposable personal income in the United States has increased, so has consumption spending. So here we have consumption spending, the dependent variable, on the y-axis, and we have disposable personal income, the independent variable, on the x-axis. So as that disposable personal income increases from $10,000 to $10,500 to $11,000 and so on, consumption spending increases from $9,500 to $10,000 to $10,500 and so on. A linear relationship between two variables produces a straight curve, in other words, a line when plotted. And note, even a straight line is called a curve. A nonlinear relationship between two variables produces a curve when plotted. Quiz yourself. Can you tell whether the following graphs show a linear or nonlinear and positive or negative relationship between x and y? We'll do the first one together. This first graph shows a linear negative relationship between x and y. It's linear because it produces a straight line, and it's negative because as x increases, y falls. Pause the video and try to do the other three on your own. For this graph, we show a linear positive relationship between x and y. It's linear because it produces a straight line, and it's positive because as x increases, y increases. This graph shows a nonlinear positive relationship between x and y. It's nonlinear because it shows a curve, and it's positive because as x increases, y increases. And finally, the last graph shows a nonlinear negative relationship between x and y. It's nonlinear, again, because it shows a curve, and it's negative because as x increases, y falls. Slope of a line. In economics, we are often interested in determining how one variable changes relative to a change in another variable. For example, by how much does the quantity of hot chocolate change relative to a change in the temperature? If the price of coffee goes up by 50 cents, how will the quantity demanded of coffee change? If one new worker joins my company, by how much will he or she add to production? And we can measure this by calculating the slope of a curve. By definition, slope measures the change in the dependent variable relative to a change in the independent variable. And it really tells us how steep a curve is. And for now, let's learn how to calculate slopes of a straight line. The slope of a straight line is measured by dividing the rise between 2 points on the line by the run between the same 2 points. In equation form, the slope is equal to rise over run, which is the same as the change in y divided by the change in x, which in our example would be y1 minus y0 divided by x1 minus x0. In other words, the change in x is this area here, and the change in y would be this area. And the neat thing is that because the slope is constant along a straight line, we can choose any 2 points that we want. Let's go through an example. This is figure 1a.4 from the text, and it shows a demand curve for pizza. So here we have the price of pizza on the y-axis, and we have the quantity demanded of pizza on the horizontal or x-axis. When the price of pizza decreases from $14 to $12, the quantity of pizza demanded increases from 55 per week to 65 per week, and these coordinates are shown here on the graph. Remember, the slope is equal to the change in the value on the vertical axis, that change in y, divided by the change in value on the horizontal axis, that change in x. Therefore, in this example, the slope is equal to the change in the price of pizza, which is 12 minus $14, which is equal to negative 2, divided by the change in the quantity demanded of pizza, which is just 65 minus 55, or 10. So, we can say that the slope of this line equals negative 2 divided by 10, or negative 0.2. Let's go through another example. Consider again our data about temperature in hot chocolate. We want to know how the number of hot chocolates change when the temperature increases from 20 degrees to 30 degrees. So when the temperature is 20 degrees, the number of hot chocolates sold is 55. When the temperature is 30 degrees, the number of hot chocolates sold is 45. So let's calculate the slope. Again, the slope is equal to the change in y divided by the change in x. Our change in x is going to be 30 minus 20, which is equal to 10. And our change in y is going to be 45 minus 55, which is equal to negative 10. So our slope is equal to negative 10 divided by 10, which is equal to negative 1. Let's consider the same data about temperature in hot chocolate. However, this time we want to know how the number of hot chocolates change when the temperature decreases from 20 degrees to 10 degrees. So when the temperature is 20 degrees, we know that the number of hot chocolates sold is 55. And when the temperature decreases to 10 degrees, the number of hot chocolates sold increases to 65. So what's the slope between these 2 points? Well, our change in x is going to be 10 minus 20, which is equal to negative 10. And our change in y is going to be 65 minus 55, which is equal to 10. Our slope, again, is the change in y divided by the change in x, which in this case is equal to 10 divided by negative 10, which is negative 1. So it's the same as it was before, because again, the slope along a straight line, no matter which 2 points you choose, is always going to be the same. So what this tells us is that on average, when the temperature increases by 1 degree, the number of hot chocolates sold falls by 1. Quiz yourself. Now consider the graph only that shows the relationship between temperature and lemonade sold. We want to know how the number of lemonades sold changes when the temperature increases from 20 degrees to 30 degrees. In other words, what's the slope of the line? So we know that when the temperature is 20 degrees, that the number of lemonades sold is 10. And then when the temperature is 30 degrees, the number of lemonades sold is 15. Therefore, our change in x is going to be 30 minus 20, which is equal to 10. And our corresponding change in y is going to be 15 minus 10, which is equal to 5. Let's plug those values into our slope equation. Remember, our slope is equal to rise over run, which is the same as saying the change in y over the change in x. In this case, it's equal to 1/2. And no matter what 2 points you choose on this graph, you should always come up with a slope equal to 1/2. So I encourage you to try that out. Graphs that depict numerical information. Graphs that depict numerical information are used to summarize and display data without assuming an underlying causal relationship. And there's 4 types. There's bar graphs, pie charts, time series, and scatter diagrams. Bar graphs use bars of various heights or lengths to indicate values of a variable. Pie charts show the share of a total amount of a variable that is accounted for by various components. This is figure 1A.1 from your textbook, and it shows an example of a bar graph and a pie chart. So again, values for an economic variable are often displayed as a bar graph or as a pie chart. In this case, panel A shows market share data for the U.S. automobile industry as a bar graph, where the market share of each group of firms, the big 3, Japanese firms, Korean firms, and European firms, are represented by the height of its bar. Panel B displays the same information but as a pie chart, with the market share of each group of firms represented by the size of its slice of the pie. A time series graph has dates on the horizontal or x-axis and the values of a particular variable that occurred on those dates on the vertical or y-axis. This is figure 1A.2 from the textbook. Both panels present time series graphs of Ford Motor Company's worldwide sales during each year from 2001 to 2010. Panel A has what's called a truncated scale on the vertical axis, while panel B does not. The slashes represent the truncation, and that just means that some numbers are omitted. So in this example in panel A, we see that we jump from 0 to 5.0. As a result of this truncation, the fluctuation in Ford sales appear smaller in panel B than in panel A. So whenever you're looking at time series graphs amongst other graphs, you should notice whether or not the vertical axis has been truncated. And finally, scattered diagrams show points that correspond to actual observations of x and y variables. So in this case, we see these points in blue. And a curve here in solid red is usually fitted to the points to help illustrate the relationship that we see. When graphing data from the real world, it's often more difficult to determine if one variable actually does cause another, which can lead to inaccurate interpretations. So the biggest 2 concerns I have are omitted variables and reverse causality. An omitted variable is an unobserved variable that, through its influence on other variables, creates the erroneous appearance of a direct causal relationship among those variables. In this example, we see a graph that shows us a positive relationship between the number of pirates in the world on the x-axis and global average temperature on the y-axis. Taking this graph just at face value, one may mistakenly interpret this as a causal relationship, saying that higher global average temperatures are caused by increases in the number of pirates worldwide. However, there is more than likely some other variable that is causing global average temperatures to increase, and it's just not represented here on the graph. Some of you may already be familiar with this correlation does not imply causation phrase. Reverse causality means coming to the erroneous conclusion about which is the dependent variable and which is the independent variable. So here we have a graph of GPA on the y-axis and hours spent studying on the x-axis, and we may mistakenly conclude that the higher the number of hours spent studying, the higher is the GPA. But is it true that the number of hours spent studying causes an increase in his or her GPA? Or is it maybe that a high GPA causes a student to study more? We have to be careful of these sorts of things when we look at numerical graphs.